Hi everybody. So first of all, we're going to do a problem that talks about the slope of a secant, but I kind of need to talk about what a secant is. And so what I've done is I've taken a circle and we're going to do everything off this point. This is our fixed point. In calculus, which is where this is supposedly heading, is that you do have this fixed point and you're looking to try and figure out what's happening as we get closer and closer and closer to it. And eventually you get to this point where you get the slope of the tangent. And it's an idea of it looks like it's getting closer and closer, so we get to say that that is the slope of the tangent. So a secant cuts through a graph in 2 points. A tangent just touches. So this tangent should be like drawn there, going across, but it gets muddied. So I just did secant and then secant and then secant and then secant. And if you notice, this point's fixed. This is our fixed point. But these keep getting closer and closer in. All right, now, how does that apply to the problem that I'm trying to demonstrate? So real quick sketch. So first of all, this is the function. And this is the actual graph if I did my scale about right. So I decided to try and show you that I morphed my scale. I made my steps on my x-axis really large. And so here is that fixed point, and I'm taking this secant up there, and then I'm going to take another secant, and then another secant. Eventually, we're going to figure out what the slope of the tangent is right there. Okay? Now, really the graph should look like this, but it's hard to draw tangent lines and secant lines on that graph. So I squished it a little bit. All right. So our goal is to do from 1 to 2, from x value 1 to x value 2, then 1 to 1.5, 1 to 1.2, 1 to 1.1, and so forth. And remember that the slope function is y2 minus y1 over x2 minus x1. And another way to write y2 is f of x2. And another way to write y1 is f of x1. Okay, so the first thing I did was, since we're concerned with the slope really at the point 1, that's our fixed point, that's our special point, we're going to take 1, we're going to plug it into the function, and I get a value of 5. So I take the 2, I put the 1 there, square it, and then I put the 1 there, and we get 5. Now I did all the other points. So I did f of 2, and it's 2 times 2 squared plus 3 times 2, and we get 14. And then I did 2 times 1.5 raised to the second power plus 3 times 1.5, and I got 9. And then I did 2, and then I put 1.2 squared, and I have 3 times 1.2, and I got 6.48. And then I did 1.1, and I'm doing that same process, so I got 5.72. I did 1.01, and I did 5.0702, and then I did 1.001, and I got 5.007002. And the question might come up, well, why didn't we just do the x value of 2? And the problem is if I do the second point as 2 and the first point is 2, the second point is 1 and the first point is 1, what ends up happening is we end up getting 0 in the denominator, and we can't divide by 0, which is part of the reason why I spend so much time talking about domain. So now we're going to do the slope. We're going to take f of 2 minus f of 1 over 2 minus 1, which from the numbers that we got over here, that's really 14 minus 5 over 2 minus 1, which is 9 divided by 1, which is 9. And then I have f of 1.5 minus f of 1, which is 1.5 minus 1, which is 9 minus 5 over 1.5 minus 1, which is 4 over 0.5, which is 8. I'm going to do the same thing for f of 1.2 and f of 1, and I've got 1.2 and 1 in the denominator, so I have 6.48 minus 5, which works out to be 1.48 divided by 0.2, because 1.2 minus 1 gives me this 0.2. You divide that and you get 7.4. Now, if you're looking ahead on the video, you're going to start seeing that it's a fairly large jump, but all of a sudden the jumps are getting smaller and smaller, and that tends to be the case when your limits work. Sometimes limits don't work. If the function's growing really fast, the limit doesn't apply, but we're actually setting ourselves up so that the limit will work. So we're over here at f of 1.1 minus f at 1, which is 1.1 minus 1. So we have 5.72 minus 5 over 1.1 minus 1, which is 0.72 divided by 0.1, which is 7.2. And now we're going to do f at 1.01 minus f at 1. And so when we do this computation, we're left with 0.0702 divided by 0.01. 1.01 minus 1 gets that 0.01. Well, now we're at 7.02. See, we're getting closer and closer to a value, and that's what the idea of the limit is. It's getting closer and closer to a value. Now we do the 1.001, 1.001, and what we find is, when we do our computations, we have 7.002. It appears, the limit appears to be approaching 7. Okay? Now, there's a way to validate this, and we can actually do this by taking the derivative. So the notation, or one of the notations for taking the derivative, is actually this f prime, or this little dash up there. And the derivative is going to be 4x plus 3, and this you just need to kind of trust me on, but I'll show it real fast. What you do is you go this exponent times this coefficient, and you bring this exponent down by 1. So 2 times 2 is the 4. And you bring this exponent down to this coefficient, and 1 times 3 is 3. And when you drop that exponent to 0, that means the x goes away. So our function is actually 4x plus 3. And since we're trying to find the derivative at x equals 1, what that means is we're going to plug the 1 in there. So we really have 4 times 1 plus 3, which equals 7. And we go, aha, it does work. Okay, hopefully that helps. Talk to you.